Hello lovelies, this is probably one of the most important videos in your A-level chemistry. Here we are looking at moles, and we're looking at it right from the very basics. Now this video is part of a longer playlist where we take you through all of the skills that you need for your A-level chemistry. But if you don't understand moles, then accessing those later videos where we talk to you through lots of exam style questions and how to incorporate lots of different maths things is going to be really hard. Moles is one of the core things you need to understand for your A-level chemistry.
Here we're going to have a look at a few questions all about moles and Avogadro's constant. So before we start these questions, let's have a look at a little recap on what formulas we're going to need to know and what facts will come in handy here. So first things first, I would say it's very important that we know this particular formula for moles. And this is going to be the absolute bedrock of your year. So we have got moles is equal to the mass over the MR, or you might instead refer to that as RFM. It depends on your school, depends on what you've been taught previously. But we've got moles is equal to mass over the MR. And of course the mass is going to be something given to you in grams, and the MR is going to be the thing that you find from the periodic table. So it could just be the atomic mass from the periodic table, or maybe if it's a big formula like NaOH or HCl or something, perhaps in that case you might need to work out what the MR is. So these are the little facts that we're going to need to know to be able to work out the number of moles of a substance that we have. So next up, we're going to need to think about Avogadro's constant. So once we know how many moles there are in a substance, we might be asked how many particles there are in that substance. And when we say particles, it could be how many atoms, how many molecules, how many particles, how many protons. It can mean a lot of things, this substance of particles that we talk about when we think about Avogadro's constant. But what Avogadro's constant is it is the number of stuff in 1 mole of a substance, okay? So if we have 1 mole of a substance, then we have this Avogadro's number, which is 6.02 times 10 to the 23 particles of whatever it is you're thinking about. Depends on the question. So once we work out the number of moles of a substance, we may then be asked how many particles of that substance there are. And that is where Avogadro's constant, which is often referred to as Na, that's where that can come in handy. So a little formula that might come in handy is going to be the number of particles is equal to Avogadro's constant times by the number of moles. So those are the key facts that we're going to use throughout this exercise here. And throughout the year, this is really, really core knowledge. So let's really get to grips with this nice and early in the year, and then you will be flying as time goes on. So let's have a look at the first little set of questions we have here. So this little first set of questions here asks us find the number of moles of different substances. So here we're going to definitely be using that formula that says that the moles is equal to the mass over the MR or RFM. Let's have a go at these questions then. Okay, so for question part A, we're asked to find the number of moles in 5 grams of carbon. So first things first, let's write down and work out what the MR of carbon is, and that's just 12. The mass, of course, is 5 grams. So in this case, we can directly put these numbers into our formula. And we can say the moles is equal to 5 over 12, which is equal to 0.417 if we round it to 3 decimal places. So that there is our answer to part A. Nice and simple. So for part B now, we're going to want to have a look at working out the MR of carbon dioxide to start us off. So here we've got 1 carbon, so that's 12, plus 2/16 for the oxygen, and that ends up adding up to giving us 44 for the MR of CO2. The mass we know is 10 grams, so if we substitute that back into our original formula, we end up getting the moles is equal to 10 over 44, which ends up giving us 0.227, again if we round that to 3 decimal places. So there we go, so that's our first couple done. It really just relies on us being able to work out the MR of a substance and then put them into this formula for moles. So now let's look at part C. And for question part C here, we're asked to find the number of moles in 6.5 grams of H2O. So let's start off by getting the MR of H2O. That's going to involve 2 times 1 for the hydrogen plus 16 for the oxygen, which gives us an MR of 18. So because the mass is 6.5, we know that moles is equal to the mass over MR. So that ends up giving us 6.5 divided by 18. And when we put that into the calculator, we end up getting a solution equal to 0.361 for the number of moles that we have there. So let's have a look at D. This one's a little bit trickier. So here we're asked to find the number of moles in 1 kilogram of CH4. So the MR is simple enough to do. That's 12 plus 4 times 1, which just gives us 16. But the mass is 1 kilogram. Don't forget that is equal to 1,000 grams. We need to have it in grams to be able to do this. We can't keep it in kilograms or we don't have moles. So then the moles is the mass in grams over the MR, which is 1,000 divided by 16 in this case, which ends up giving us 62.5 moles. So it's only when we see like big masses, like kilograms or bigger, that we're going to notice the moles being like big numbers that aren't like smaller than 1 generally. But in this case, of course, we can see it here. So let's have a look at E, where again, there's a little bit of a twist to it. So in E here, we're asked to find the number of moles in 1 ton of oxygen. So of course, we'll start again. Let's work out the MR of O2. And in this case, that's going to be 2 times by 16, which gives us 32. But we don't have grams again, we have tons. We have 1 ton for the mass. And for this, really, we just need to know that 1 ton is equal to 1 million grams, which we could also think as 1 times 10 to the 6 grams. So when we get the moles, that's the mass over the MR. That's going to be 1 million grams divided by 32. And when we do that calculation, we end up getting a very large number of 31,250 moles. And that there gives us the number of moles in 1 ton of oxygen. So that went well. In the next part now, we're going to have a look a bit more at working out not the number of moles, but the number of atoms of substance that we have. In these questions here, to do this, we first will still need to work out the number of moles. And this is where at A-level things get a little bit trickier because you have to see the middle step without them necessarily spelling it out to you. Let's have a look now then at question 2. So for question 2 here, what our general strategy, and we will have to adapt it as we go through, our general strategy will be, let's first work out the number of moles of each substance and then work out the number of atoms. Okay, so first we're going to use our formula like we have before. Moles is mass over MR to first work out the number of moles of the substance, and then we will use Avogadro's constant to work out the number of atoms. Okay, so let's look at question 2 part A. So here we need the number of atoms in 7 grams of carbon. So let's start by working out the moles just like we did in the first part. So we know the MR of carbon is 12 and its mass is 7 grams. So that means if we use the fact that moles is equal to mass over MR, we get 7 over 12, which ends up giving us an answer equal to 0.583 moles of carbon. So now we know how many moles there are of carbon. Let's remember the relationship between the number of atoms or particles of a substance and the number of moles. And if we know that there are a certain number of moles of carbon, we can multiply it through by Avogadro's constant to get the number of atoms. Avogadro's constant is 6.02 times 10 to the 23. And if we times it by 0.583, we end up getting 3.51 times 10 to the 23. And that is the number of atoms of carbon that we have in this substance. So not too bad, okay? So we're going to use that same approach here with the next few, but we're going to see some twists. So in this particular question, we were just talking about just carbon, weren't we? Just a bulk amount of carbon on its own. But the other ones, we're going to see some molecules and little twists on it where we're going to have to think a little harder. So let's have a look now at question B and see what's going to be slightly different. So here you can see we're asked to find the number of atoms in 8.7 grams of H2. Now the thing is here, we are going to start off by working out the number of moles of H2, but we will need to remember that in every one H2, we actually have 2 atoms within that. H2, the molecule, is of course composed of 2 hydrogen atoms. So what we will need to do here is first work out the moles of H2, but then use that to work out the amount of moles of atoms just generally within that substance, which is going to be 2 times the moles of H2. And then from there, we will use Avogadro's constant. So let's get started. So question 2b here. First, let's work out the MR of H2. And in that case, that is going to be 2 times 1 equals 2. And then the mass is equal to 8.7 grams. So we can quite simply work out the number of moles of H2 by doing the mass divided by the MR. And that will end up being 8.7 divided by 2, which gives us 4.35. So 4.35 is the number of moles of H2 molecules that we have. Now, we need to have a think that if we have H2, for instance, we can break that down into its respective atoms. So H2 we could think of as breaking down to 2 H atoms. So that means that for every one H2 we have, we've got 2 hydrogen atoms. So if we have 4.35 moles of H2, then that means that we're going to have double the amount of hydrogen atoms. We're going to have 2 times 4.35 moles of hydrogen atoms. So for that reason here, we're going to need to have a look at this, work out the moles of hydrogen atoms and say, well, that will be 8.7. And then use our relationship between the number of atoms or particles of a substance with its number of moles to work out the number of atoms there actually are. So here we will take Avogadro's constant, which is 6.02 times 10 to the 23, and times it by the 8.7, that moles of hydrogen atoms that we have within this. And that will end up giving us an answer of 5.24 times 10 to the 24 atoms. So see, a little bit of a sneaky one, that one. It would be very easy just to have run through it and forgot to times by 2, but that's where we've got to be a little bit thoughtful with it. Okay, let's have a look at part C, where we're going to see a similar idea. So in part C, we're asked to find the number of atoms in 9.2 grams of C6H6. So important thing to see here is that for every one C6H6 we have, actually going to have 6 plus 6, so 12 atoms. So again here, we will begin by working out the moles of C6H6 we have, then we'll work out the moles of atoms, and then we'll work out how many actual atoms. So let's get started. Okay, let's have a look at question 2C here. So the MR of C6H6 is going to be equal to 6 times 12 for the carbon, plus 6 times 1 for the hydrogen, and that all tallies up to give us 78 for the MR of that. So we know the mass is equal to 9.2 grams, so we'll make a note of that as well. And now when we need to calculate the moles, we're going to do the mass over the MR. So that is 9.2 divided by 78. And when we do that, we end up getting an answer equal to 0.118 for the number of moles of that substance. And we need to remember, like we said, that's the moles of C6H6. Now, if we dive inside that, we can see it's made up of 6 carbons and 6 hydrogen atoms. So that's 12 atoms in total. So for every 1 mole of the C6H6, we have 12 moles of the atoms. So we need to do 12 times by that 0.118 to find out the number of moles of atoms that we have here. So when we do that, we end up getting an answer for the moles of the atoms equal to 1.416. So it's important we don't confuse that with the number of atoms, which is what we're going to find next. So the number of atoms we find by doing Avogadro's constant, which is 6.02 times 10 to the 23, and timesing it by the number of moles of that substance we're looking at. So we times it by the 1.416. And we end up getting an answer equal to 8.52 times 10 to the 23 for the number of atoms in that 9.2 grams of C6H6. Good, so I hope that's making sense. Let's have a look now at part D. Okay, let's look here at D. So first things first, let's work out the MR of ammonia, which is this NH3. So here we know that we have 1 nitrogen, which is 14, plus 3 times 1 for the hydrogen, which gives us an MR of 17. So we know the mass is 4.8 grams, so that means that we can work out the number of moles of this NH3 by doing the mass of it over the MR of it. So in this case, that's going to be 4.8 divided by 16. We'll put that into our calculators and we end up getting 0.282. Now, it's important we remember that that is the moles of ammonia, and this question, if we look back at it here, is looking at the number of hydrogen atoms. So not even any atoms, just the hydrogen atoms. So if we had ammonia, you can see it's made up of 1 nitrogen and 3 hydrogens. So for every 1 ammonia, we get 3 hydrogens, which gives us a 1:3 ratio here. So that means if we want the number of moles of hydrogen atoms, we need to do 3 times the moles of ammonia. So that's 3.0.282. And if we put that into our calculator, we'll end up getting 0.846. And that is the amount of moles of hydrogen atoms. Now, if we want the actual number of hydrogen atoms, we need to take Avogadro's constant and multiply it through by the number of moles of the hydrogen atoms. So there we'll do 6.02 times 10 to the 23, and we're timesing it by 0.846. So when we calculate that, we will end up getting an answer for the number of hydrogen atoms equal to 5.09 times 10 to the 23. And that there is our solution to part D. So let's look at this last bit, 2E. Okay, so here let's find the MR of this sodium sulfate. So here you'll see that we have 2 sodiums, so that's going to be 2 times 23. And then we're going to add 32.1, and then we're going to add 4 times 16 because that's the MR of oxygen. So we're going to put all of those into a calculator and and we'll end up getting an MR equal to 142.1. So we know the mass is 1 gram, and so we can work out the number of moles of sodium sulfate by doing the mass over the MR, which of course in this case is equal to 1 over 142.1. And putting that into our calculator, we get 0.007. Now, if we look over at this question again here, you can see we're looking at the number of sodium ions. We're not even looking at atoms. So here, when we think about how sodium sulfate can dissociate, let's not think of it in terms of atoms, but in terms of ions. And we know it can split into 2 Na+ ions and a sulfate ion. Now, what really matters there is the ratio between the sodium sulfate and the sodium ions, which is a 1:2 ratio. So for that reason, we can work out the number of moles of sodium by saying it's 2 times the number of moles of sodium sulfate. So, of course, we know how many moles of sodium sulfate we have, so we can just do 2 times that 0.007, and we end up getting 0.014 for those number of moles of sodium ions. So now we need the actual number of ions, not the number of moles, but the number of ions. So to find that, we're going to take Avogadro's constant, and we're going to times it by that number, the amount of moles. So we've got 6.02 times 10 to the 23 times by 0.014. And that ends up giving us 8.428 times 10 to the 21 sodium ions. And that there is our answer to question E. So this last little set of questions are mixed. So this is to really test if you've understood what we've been looking at here. Let's have a look at part A. So for this one here, we're told that we need to find the mass of 2 moles of sodium hydroxide. So we're still going to use our formula that moles is mass over MR, but in this case we're going to rearrange it, and we're going to say that mass is equal to moles times by the MR. So for this reason, we do still need to work out what the MR is of sodium hydroxide. So the MR of sodium hydroxide is going to be equal to 23 for the sodium, plus 16 for the oxygen, and plus 1 for the hydrogen. And that all adds up to give us 40. So if we want to find the mass of 2 moles of this sodium hydroxide, it's going to be 2 times 40, which will give us 80 grams. And there we go. We have the mass of 2 moles of sodium hydroxide. So now this one's a bit trickier. We're asked to find the number of atoms in 1 ton of ethanol. So we'll start off here by working out the MR of ethanol. So here we can see we have 2 carbons, we actually have 6 hydrogens and 1 oxygen. So we're going to do 2 times 12 plus 6 times 1 plus 16. And that is going to give us the MR of ethanol. And that should give us 46 for the MR. For the moles, we know that that is mass over MR, so we also need the mass. So the mass in this case is 1 ton. Now we mentioned this in an earlier question. We need to know as chemistry students that 1 ton is equal to 1 million, or 1 times 10 to the 6 grams. So we're going to use that now to work out the number of moles. So moles is the mass over the MR. So that's going to be 1 times 10 to the 6 divided by 46. And that gives us 21,739 moles. And that is the moles, don't forget, of the ethanol. So now, if we look at the question, you can see we want the number of atoms in 1 tonne of ethanol. Now here we need to think, well, if we have 1 ethanol, how many atoms are there in 1 ethanol molecule? So if we look at this, we can see that we have 2 carbons, we have 6 hydrogens, and we have an oxygen. So for every 1 mole of ethanol, we're actually going to have 9 atoms within that mole. So we've got 9 moles of atoms for every 1 mole of ethanol. So we have a 1:9 ratio going on there. So that means that the moles of atoms is going to be equal to 9 times that 21,739, which I make a very large number. I make that 195,651 moles of atoms. Now, to get the actual number of atoms, what we need to do now is times that number by Avogadro's number. So the number of atoms is going to be 6.02 times 10 to the 23, and we're going to times that by the number of moles of atoms that we have. So, definite job for the calculator there. I end up making that 1.178 times 10 to the 29. And that is the number of atoms in 1 tonne of ethanol. So finally here, we're asked to find the number of moles in 7.5 grams of carbon. So MR of carbon is simply 12, and the mass is 7.5 grams. So back to basics here, we know that moles is equal to the mass over the MR. So in this case, we'll do 7.5 divided by 12. And that there is going to give us the number of moles of carbon in 7.5 grams of the substance. So I make that to be 0.625 moles. So there we have it. That is that worksheet on moles and Avogadro's constant. I hope you're feeling a lot more confident now on it and ready to give some harder questions a go. Good luck.
Ouch! This is why in some videos I've explained scratches.